So yeah, we were just talking about the dark side. So let's move to the dark side in this room a bit. I come from theory. That's the dark side. So I'm going to do a bit of PR about what I'm calling path representations. This is still work in progress. The submission is being finished at the moment, but the work is not yet submitted, and it's joint work with several people. So what do we want to talk about here? Actually, this is a conceptual thing that I want to introduce. I hope that it will be useful at some point in processing graph queries, and it originated from a couple of challenges or maybe issues that I thought I could foresee based on what I have currently seen in all the variants of the spec, right? So what do I think are a couple of challenges in graph queries? Well, first of all, exponential output. I mean, the output of a query can become very large, even for very simple queries. Yeah. Suppose, for example, that you take this simple query. What does it do? It goes from A nodes to B nodes, and it matches all the shortest paths. But then it wants to return the end nodes of the paths and also the paths between the nodes, right? So if you evaluate this query on this graph, well, then, and you represent your result as this table, essentially this table has one row for every path in your result, well, then you have 2 to the n many rows in your table, right? On a graph with O of n many nodes of edges. So this is a huge output, and this is exponentially larger than the endpoints that we've been considering in academic research for 30 or so years. And it's also more than the endpoints that you get in Sparkle, right? So this is a very, very large output. Okay, another challenge, kind of, is some kind of composability stuff, yeah? I mean, in graph query languages, as I'm seeing them now, or GQual, SQL, PGQ, the input is conceptually a graph, right? And then you run a query, and then what comes out, as far as I can see, conceptually, this is a table, yeah? And then, yeah, the question is, yeah, if you want to continue querying this, what do? You now don't have a graph, right? So the thing here on the bottom, it conceptually looks a bit cleaner. What I mainly want to say here, I know that there are methods of turning graphs into tables. Yeah? I know that this exists. You have graph projections in Cypher, for example. But I want to make clear here that this is some kind of challenge, and it exists on 2 levels. First of all, it exists on a level where you want to run an entire query on a graph, and then you have the output of your entire query, and then maybe you want to run another query on this output later on. So this is like a meta level. But you also have this on a deeper level. Inside your query plan, you have to figure out for individual, let's say, relational algebra operators, how you are going to represent your output of parts of the query plan. What are you going to feed to further upstream operators in your query plan? How are you going to represent this output? Yeah? Are you going to stick with this representation that the specification is currently giving you, or are you going to think about something else that maybe can represent all this stuff a bit more succinctly? Okay, third challenge. Okay, this is not our focus, but maybe we can help a bit here. This is, yeah, how do you represent output for users? Yeah, you have a query which produces a possibly huge table, as we have seen, it's exponential. How do you make this digestible for users? Yeah. I know that there are graph projections. They look nice, but this is not a lossless representation of the output of your query, right? So here, let's take a very simple example. This is a cycle of length 3. Now, suppose that I run a query and I want to find the shortest even length path from A to A, right? This is a path of length 6, right? You start in the node A, then you go to B, to C, back to A, then back to B, back to C, and then now you have a path of length 6 from A to A, right? Yeah, and this is the path that you store in your table. If you computed the graph projection of this path, well, you basically project it back on your graph, and now you again have this thing of length 3, which means that I don't know how these systems really work. Yeah, but to me, conceptually, it seems like you're losing the information that you have gone through this round twice. If you would take this graph on the right straight as an input for another query, and now you ask, does this output of this previous query have a cycle of length 3? You would get yes, yeah? But you should get no, because you just, in the first query, asked for all the even length paths, okay? Good, so these are a couple of challenges that I've seen when just looking at these, all these specs from a high level. And now what do we want to do? Well, we want to present an idea that may help here in these things a bit, or yeah. Our focus is on one. So our focus is really on, suppose that you want to represent a set or a multi-set of paths. How can you do this much more succinctly than this table, which essentially just lists one path, one after another, okay? So, yeah, exactly. Our representation, it can never be larger than the table, and it is lossless as opposed to graph projection. So, and now I want to give you the main idea in a couple of examples, and this will build up a little bit. So suppose that you have this query and this graph, yeah? So the graph is very simple, and the query just asks for paths from an A node to a B node, right? Well, in our representation of all the paths that you would have in the output is just this graph that you have on the right, plus the information that in this graph we are storing all, we mean all the paths from A to B, yeah, and that's it. From this example, it looks like we're only thinking about subgraphs, but this is not the case, yeah. So now suppose that we want to represent all the paths from A to A that have even length, yeah. In our representation, this would be all the paths from A1 to A1 in this graph here, yeah. And now you also see that these the nodes that you see on the right, there is a correspondence between the nodes on the right and the nodes on the left, right? An obvious correspondence, I hope. So every node, for example, B1 corresponds to B, and B2 also corresponds to B, right? So here on the right, you are actually encoding that you're going through this cycle on the left twice. Okay, so conceptually, okay, this is a bit of a technical slide. Conceptually, I think what I want to bring forward is actually something very easy. A path representation consists essentially of 3 parts. The first part is just an unlabeled graph. It can be any unlabeled graph. It doesn't have to be a subgraph of your graph. The second thing is a homomorphism, and this homomorphism tells you which node of your graph in the path representation corresponds to which node of your actual data graph, yeah? And then the third and the fourth thing, okay, maybe it's 4 things, but you have a set of start nodes and a set of target nodes, yeah? And now this thing represents a whole bunch of paths. And which paths does it represent? It represents all the paths from some node in S to some node in T, okay? And now you still have paths in R and not yet paths in your graph. But when you apply your homomorphism, then you get a path set of, or a multi-set of paths in your graph. And this is the main idea. Okay, and it's a lossless representation of one of these things. So let's just revisit this, yeah? So the example that I just showed are, so the even length paths from A to B here, for example, in our path representation, it would look like this. So the start nodes, every start node has a small incoming arrow, and every target node has like a double box, okay? And so, yeah, so here you see on the right what this thing looks like. And then the naming of the nodes, this is what the homomorphism does. All right, you can represent multi-sets, yeah? Because what are you seeing here on the right? If I say, look, I'm representing every path here from a start to a target, yeah, I have this path A1, B1, C. Which path does this correspond to in my original graph? Well, it's ABC, right? That's what this is mapped to with the homomorphism. And then the second path, A1, B2, C1, it also corresponds to this path. So I'm representing with this thing on the right, I'm representing this one path on the left twice. Good. So yeah, and And indeed, if you use this to represent these exponentially many paths in your graph, then, I mean, your representation size is linear instead of exponential, what we had before. Good, how do I think that something like this could be useful? Well, if you have your graph database and your query and you want to evaluate it, well, I think you can use path representations to represent multi-sets of paths in intermediate results, and this can just make the size of intermediate results exponentially smaller as opposed to if you would store every path separately. Okay, and then from these path representations, you can produce your output. You can generate your table or you can produce your graph projection, and this is something you can do. And by the way, if at any point you want to, in your computation, you would want to go back and forth between, let's say, a multi-set of paths or a path representation, well, you could just do that. You can compress your set of paths or multi-set into a path representation, or you can decompress. And now, of course, until now, I just explained you an idea, but what we are currently doing actually, and this is the main bulk of the paper, is we are exploring lots of computational properties of these things. Yeah, now what can you do when you actually want to compute with these things? Yeah, okay, I don't have time to go over all of this, I can see. But we look at expressiveness. So a path representation can represent any finite multiset of paths. It's never larger than the table, as far as I can understand, but it can be exponentially smaller. Yeah, and you can compute the table back from the path representation. And how much time does this cost you? Well, I think essentially linear in the size of the table. So it doesn't cost you any extra work. I mean, from a theoretical perspective, it looks good. Path representations can be optimized. I mean, you can start with just a set of paths and then try to compress this into a very small path representation. Now, if you have two, what are interesting questions from a theoretical point of view here? Well, if you have two different path representations, you want to be able to decide, do they represent the same multiset of paths? That's like, for theoreticians, that's like very closely related to optimization. This can actually be tested in polynomial time in the size of the path representation. It may sound a bit unintuitive if you think about this from a theoretical point of view. It sounds a bit like non-deterministic finite automaton equivalence, which is p-space complete. But here we are not asking for this automaton equivalence. We are asking for if every run has if every word in the language has the same amount of accepting runs, and this is actually polynomial time. It's non-trivial. That's a non-trivial result. Okay, doing the real true minimization is NP complete, but remember that we're working here with something that's exponentially succinct. If you would work with the table, you're working with an object that's exponentially larger anyway. Okay, so I'm wondering if this thing can be a viable option for representing paths in intermediate results for graph queries. So we've also studied how this can actually be used. I mean, until now, I'm just talking about representing sets of paths. Yeah? So we've gone deeper and dug into how you can actually answer queries doing this. So for regular path queries, well, if you have a regular path query, you can compute the path representation or a path representation for the set or for the set of paths in its output in linear time. And if you want to do this with the table, it costs you exponential time because you can have exponentially many paths. Yeah, you can get immediately. I mean, if you can avoid this table representation in the middle, if you're only interested in the graph projection in the end, you can go from start to end in linear time instead of exponential time. Yeah, so it seems promising. And in our draft paper, we study path representations for regular path queries under all these different evaluation modes that you have. That the standard supports, and these things can even represent infinitely many paths with a finite representation. And I mean, from a very academic point of view, I'm also wondering a bit about if this can help you extend the language in some way, so that the query language can actually deal with infinitely large intermediate results that you can actually present in a finite way. But that's a whole other level. Okay, let's move fast forward a little bit. If under different evaluation modes, these complexities need to be tweaked a bit. Yeah, and then of course, if you have a path representation, You can do, I mean, we started looking at doing simple aggregation stuff with that. You can count the number of paths in this thing in polynomial time. You can uniformly sample a path of length n in polynomial time. We are thinking beyond regular path queries, of course, because regular path queries are just a very simple building block of graph pattern languages. So we're thinking about what can you do with unions of regular path queries, actually, because we concern multiset semantics from the start. These are very easy to deal with. We tweaked our definition so that this becomes easy and it works. And then, yeah, of course, once you start doing conjunctive regular path queries, things start becoming really, really interesting. Yeah, and this is, we are looking into that. And we're looking at how to efficiently answer queries like, let's say this thing. I mean, here you want to match some kind of pattern on your graph. You bind some node to X and you bind some other node to Z. And now you want to just project out the result. You want to have the pairs X and Z. And of course, you want to have the correct cardinality, right? So the counting problem inside the brackets here determines how often you have to return a pair of nodes. And okay, we're thinking about how you can use path representations. Yeah, let me fast forward to do this efficiently, avoiding all these exponential steps that you would have if you would just store your set of paths as an explicit set of paths. Yeah. Okay, I'm going over this. This is out of scope. Yeah. And a final thing I want to say is that when you start evaluating conjunctive regular path queries, you open interesting new space that I have not seen before for optimizing how you store even path representations. Here, for this example here, this represents, let's say, all the paths that go from the yellow area to the green area. Yeah, so all the paths from S to T, right? But you can use different representations for this set of paths. You can represent it like this, but then if you would need to compute afterwards your set of endpoint pairs, you need to do some computation, right? I mean, for this top A node on the left, well, only the top right B node corresponds. So you need to do again a reachability test to find out the binary relation of start and end nodes that correspond to each other. Yeah, and you can compute another path representation for the same set of paths from which you can get these endpoint pairs much more efficiently. So here you just have, I mean, here you immediately know which node on the right corresponds to this node on the left, and on the bottom the same. Yeah, but this comes at a trade-off. Going from the top kind of representation to the bottom kind of representation, it can cost you, in the worst case, quadratic time. So we're thinking about in which cases you can avoid this when evaluating CRPQs. Okay, good. I realized that I was indeed on the dark side, and this was probably a bit more technical than most of the other talks that we have seen before, but I just want to bring this out here as something that I think can be conceptually interesting. Okay, thank you.
Thanks, Wim.
Hi, Wim. Me again.
Hello.
Thanks for the interesting talk. Well, welcome in the LDBC TUC meeting. I didn't say that before. And given that you are in the LDBC meeting, LDBC actually has previous work on the design of query languages. You mentioned those and the role of paths in those query languages. I'm referring to the paper G-Core.
Yeah.
So you may be aware, but maybe not everybody here is aware that, well, G-Core did a number of things, but one of the more controversial things that also did not end up in the proposed standard GQL is the inclusion of paths as a first-class citizen in the language, because G-Core said or advocated for not the property graph model, but for extending this to the property path graph model.
Yeah.
Of path property graph model. That was it. Excuse me. But yeah, it would follow, of course, your table approach, because it's it would define a set of paths as part of the model, and those paths would be sequences of edges that actually exist in the graph. Graph is v, e, so it must be from there. Anyway, so in that sense, it has all the nasty properties of exponentially large amounts of potential results and all that. And so your work is interesting, and it's kind of rekindled my my interest in the fact that we probably need such a thing, or that we would like to have also but databases of paths and returning paths, and your work could be an optimization in the sense that it would be a compact way of representing such paths.
Yeah.
Because, well, you started, of course, in your motivation by saying, okay, we cannot even return paths of length 6 because you would see something that has length 3 and you cannot really remember this, and the way that you represent this fixes this. But G-core would be able to return paths of length 6, but it would be potentially exponentially many paths of...
yes, what I meant is that if you take the graph projection of the tabular result, as I understand it, as is currently in GPL, then you have
a naive graph projection would
exactly
lose the information that you had to traverse this twice.
Yes, that's something else.
Okay, but I was thinking in G-core, no. You could have at least represented these paths of length 6 correctly.
Yes, fully agree. Yeah. Actually, G-core was the first inspiration to this, and the first thought that triggered this was, okay, how are you going to represent these paths in G-core? And the first step to this kind of work was, okay, let's find a way to represent these G-core paths that you have just in a more compressed way. But then, of course, the whole language came on, and we noticed that it had a similar problem as G-core, and this is where we are now. Yeah.
But I did have a remark, because in the end you said, well, we have this example, and you had S and T, and there were like 2 S nodes that would be connected by various paths to T nodes.
Yes.
That you had to remember that some of them, that only the upper S node was connecting to the upper T node, and the lower with the lower T node.
Yeah.
And you said, well, then you would have to do a reachability test in order to properly. But now comes my remark.
Yeah.
The general principle here for G-core to advocate for returning paths is that paths may be answers of queries.
Yeah.
And queries are not only full reachability queries, but they can have, for instance, also predicates.
Yeah.
So it could be that you're interested only in certain paths, a subset of all paths.
Yeah.
And and therefore it is not like that afterwards you can just find out which S's and T's should be really in this result by doing reachability tests. No, you actually have to explicitly remember this, because there could also be connected S and T nodes that we do not want to represent as paths.
Yeah. We thought about this. So the thing is the following. For the same multiset of paths in your graph, you can use different path representations. And so this thing on top of the slide, this would be one representation for some multiset of paths in your graph. What you're seeing here on the top, this is not a subgraph of your graph, right? You still have this homomorphism that says which nodes on the picture correspond to which nodes in your graph. Yeah. And then this thing on the bottom, this is a representation of the same thing. But now, for example, but it does it less efficiently. Now I can go from this thing here to the G-core representation by simply saying, look, let's take this path, and that's one path, and you just unfold everything. Yeah. And this is still a path representation of the same multiset of paths. Yeah. But what I'm saying,
I understand that. I was just. I mean, this solution that you have down here is less desirable because it replicates a number of nodes. It replicates those B nodes and this shared path. So it's not as succinct as it could have been. And I think that was my thought. My other thought was, well, we can in fact use your ideas to indeed represent paths, because these are effect graphs. You could kind of simulate or use graph technology to to represent these as graphs, special graphs for meta graphs that would have annotations. You can actually annotate what is a starting node and what's an end node, but you can also annotate combinations of starting and end nodes. By saying, and that would be actually a more succinct way of doing this. You can also, exactly. You could also just add a binary table that says which corresponds to which. So yes, and this is what I mean. Or use properties for that.
Exactly, and this is what I mean that you have this with this remark where I meant that you have this interesting space to start exploring optimizations, because you have a very big number of path representations that you can use for the same paths. And now you can just choose how succinctly do you want to make this, possibly at the cost of later computation that you need. If you're later just interested in, I don't know, sampling or counting the number of paths in your answer, then it's totally fine if you group your start nodes and your end nodes, if you would do something like that. If later in your query plan you would actually need the pairs of start and end nodes as pairs as they correspond to each other, well, then you may need another representation, but this may cost you a little bit extra space in intermediate results. So what I think that this essentially is, or one thing that this is essentially is a generalization of these paths that you have in G-core, but you can compress them together, and we're kind of studying these representation size trade-offs that you get when evaluating queries.
Two quick questions. So one is wearing my WG3 hat, and if you look at GQL or PGQ, so the output is not a path, it's a path together with bindings of variables, which could be singleton variables and group variables. And how do things get affected by that?
We don't know yet. That's the part where I say, look, this is a conceptual idea that looks at this point very promising from a theoretical point of view, but there is definitely also other work that we still have to think about, and that would be one of these things. I'm aware of that.
And wearing my theoretician's hat, so more than a decade ago with Pablo and Peter Wood, we had this automated, when we looked at ECRPQs, extended CRPQs, we looked at automated representations of path. And also achieved with that, we could achieve exponential reduction. Is there any connection with our automated representation from that Todd's paper?
Now, your paper is on the radar. We have it in our list of related work things. I remember that we have discussed this, but I don't remember the outcome. I would have to take this question offline, I think. But we have looked at it. As I remember, you were looking at tuples of paths, right? And this is not at all about tuples of paths. Okay, yeah, sure. Yeah. Okay, but I would have to take another deeper look.
So, a couple of thoughts. First of all, in terms of the purpose of this compressed representation, when it's actually useful, it seems to me that it's only useful if you can actually carry out operations on it, if you can actually treat it as an operand, because the way that the result of the query escapes for use is either, I think, as the graph projection, because then we're just in a composition of operations over graphs, and that's what we want to do. Or we want to actually see the unwound paths in order to process them one by one. And neither of those is helped by this compressed representation. Whereas if they're, going back to the G-core paper point, if there are operations that you want to carry out on sets of paths, and by the way, I think calling this a path representation is misleading. It's a path set representation.
Multi-set, actually.
Or it's a multi-set representation, yet. I mean, I think that would actually be useful to name it.
Yes, but path representation abbreviates to PR, which is...
Maybe so, but it relates to the point. It relates to the sort of substantive point I'm making, which is that if you want to operate on multi-sets of paths that are knowably the result of a query, effectively, then I guess they don't have to be that, but that would be a likely cause of their origination. Then then this becomes very important.
Yeah.
Otherwise, you know, yeah, I can see it might actually be just like almost like a compression mechanism,
Yeah.
you know, in a processing pipeline, but by the time you've finished, it's going to get expanded.
Yeah.
The other point that the other point I was going to make escapes me, so I'm going to have to shut up. If it comes back to me, I'd like to raise it.
Did the first one require an answer? Because I completely agree with you, and this is also completely how we envision this thing. We want to have some kind of lossless representation of whatever you would store in the table otherwise, yeah, and something that would just help you getting smaller intermediate results of queries, and maybe due to the fact that this still, I don't know if this will work, but maybe due to the fact that this kind of representation mechanism is still a graph, maybe it can also help somewhere here and there in composability questions, right? But primarily it's intended as something to losslessly compress whatever you would do otherwise in the table.